Welcome to the number universe. I'm so glad you're here. Today we are starting a journey that will completely change how you think about numbers. What if I told you that numbers have a family tree? That there are different types of numbers, each one special, each one with its own story. Some numbers are simple and whole, others are broken into pieces, and some numbers are impossible to pin down completely. In this foundation arc, we're going to explore every branch of that tree. We'll start with the numbers you know best and work our way to numbers that might blow your mind. Ready? You've been using numbers your whole life, since you were a tiny kid, counting on your fingers, playing with toys, buying things at a store. But here's the mystery. Some numbers have a secret, they go on forever, and they never ever repeat. What number could possibly do that? Let's find out. Let's start at the very beginning. Before we talk about anything fancy, we need to understand natural numbers. Natural numbers are what you use when you count 1, 2, 3, 4, 5, and so on. They never stop. But notice something important. The line starts at 1, there is no 0 here. Natural numbers begin at 1, not 0. Why? Because when you're counting things in the real world, you count one object, two objects, three objects. You don't count 0 objects and call that counting. 0 comes later in our story. For thousands of years, humans only had natural numbers. But then a big problem emerged. Imagine you're a merchant with 10 sheep. You sell all 10. How many do you have left? The number 1, 2, 3 don't help. You have nothing, but nothing needs a name. That's when the Indians invented 0. Not just as empty space, but as an actual number, 0. Now we could represent nothing. And with 0, something else became possible, positional notation. The difference between 10 and 100 suddenly made sense. So far we have whole numbers 0, 1, 2, 3 and so on. But the number line only goes in one direction. What if we need to go backwards? Think about temperature on a cold winter day. It might be 10 degrees, but it can get colder. What about minus 10 degrees? That's below 0. Or think about money. If you have $5, great. But if you owe $5, you have negative $5, you're in debt. These negative numbers are real. They fill the left side of the number line. Now we have integers, all the whole numbers plus all their negatives, the complete line stretching left and right forever. Let's start with something familiar. Imagine you and your 7 friends share a pizza equally. Each person gets one slice out of 8 pieces total. That one slice out of 8 is what we call a fraction or a rational number. The top number is called the numerator, telling us how many pieces we have. The bottom number is called the denominator, telling us how many equal pieces the whole is divided into. A rational number is any number that can be written as p over q, where p can be any integer and q can be any integer except 0. We can't divide by 0, ever. Here's something important. Every integer is also a rational number. The number 5, that's 5 over 1. Negative 3, that's negative 3 over 1. Every integer can be written as a fraction with 1 in the denominator. Now let's look at positive and negative fractions on a number line. 3/4 sits between 0 and 1, 3/4 of the way across. Negative 2/3 sits to the left of 0, 2/3 of the way toward negative 1. Between any two numbers on the number line, no matter how close they are, there are infinitely many rational numbers. Watch what happens when we zoom in on a tiny section. This property is called density. Rationals are so densely packed that between any two rationals, there's always another rational hiding in between. Yet strangely, there are enough gaps left over for an entirely different type of number that we'll discover soon. When we divide 1 by 4 using long division, something interesting happens. We get 0.25 and then the division stops. These are called terminating decimals because the digits come to an end. Another example, 1 divided by 5 gives us 0.2. Again, the division stops and we have a terminating decimal. When can we get terminating decimals? It happens when the denominator only has prime factors of 2 and 5. Now let's try something different. 1 divided by 3. Watch the long division carefully. 1/3 equals 0.3 repeating forever. The digit 3 repeats infinitely. We call this a recurring or repeating decimal. Here's another example. 1/7 produces a 6-digit pattern that repeats forever. Rational numbers with prime factors other than 2 and 5 in their denominator always produce recurring decimals. The remainder cycles back to a previous value, forcing the digits to repeat forever. Here's the key rule about rational numbers. Every single rational number must have either a terminating decimal expansion or a recurring decimal expansion, period. No exceptions. This is a mathematical law. Now, what if we tried a decimal that never ends and never repeats? A decimal like 0.123456789101112, where there's no pattern at all. That would violate the rule. Such a number cannot be rational. These strange decimals that never end and never repeat are called irrational numbers, and we are about to discover why they're so important and so mysterious. You've learned that rational numbers are all numbers that can be written as P over Q. They're dense, they're everywhere, we use them constantly, but there's a secret. They don't fill the entire number line. There are gaps, and in those gaps lie strange numbers called irrationals. An irrational number is a real number that absolutely cannot be written as P over Q. No matter what integers you choose for P and Q, you will never equal an irrational number. It's impossible. The three most famous irrational numbers are square root 2, square root 3, and pi. Let's look at their decimal expansions. Here's square root 2, 1.4142135623733095. And this keeps going forever. Look for a pattern, any pattern at all, you won't find one. The digits appear completely random. Let's compare. Here's the rational number 1/3, 0.333333. See the pattern, 3 repeating forever. Beautiful simplicity. Now look at pi, 3.141592653589979. Here's a profound question. How can these numbers be real? How can they exist on the number line if we can never write them down completely, if we can never express them as fractions? Irrational numbers are infinitely numerous. In fact, there are more irrationals than rationals. Even though rationals are dense and infinite, irrationals are a higher level of infinity. They fill the gaps that rationals leave behind. Between any two rational numbers, no matter how close they are, there is at least one irrational number. And between those more irrationals, they're everywhere yet invisible, impossible to write, yet impossible to escape. We're going to prove that square root 2 is irrational using a technique called proof by contradiction. We'll assume square root 2 is rational and show that this leads to an impossible situation. If square root 2 equals p over q, then we can square both sides. Square root 2 squared equals p over q squared. The left side becomes 2, the right side becomes p squared over q squared. Now multiply both sides by q squared. We get 2 times q squared equals p squared. Look at this equation carefully. The left side is 2 times q squared, the right side is p squared. Now 2 times q squared is definitely even because it's 2 times something. Any number multiplied by 2 is even. If 2 times q squared is even, then p squared must also be even. Since they're equal, they must have the same property. And if p squared is even, what does that tell us about p itself? Here's the key insight. If p squared is even, then p must be even. Why? Because if p were odd, then p squared would also be odd. Odd times odd is always odd. So if p squared is even, p cannot be odd. Therefore p must be even. Since p is even, we can write p equals 2r for some integer r. Now substitute this back into our equation. 2 times q squared equals p squared becomes 2 times q squared equals 2r squared. Divide both sides by 2. we get q squared equals 2r squared. Now look at this equation. 2r squared is even. So q squared must be even, and if q squared is even, by the exact same logic, q must be even. Wait, stop. We have a serious problem. We started by assuming p and q were in lowest terms, meaning they share no common factors, but we just proved that p is even and q is even. They both have 2 as a common factor. This is a contradiction. Since we reached a contradiction, our original assumption must be false. Square root 2 cannot be written as p over q. Square root 2 is irrational. This elegant proof, discovered by ancient Greek mathematicians, shattered their world. They believed all numbers were rational. This proof proved them wrong. The ancient Greeks couldn't solve irrational numbers algebraically, but they had a genius geometric method. They could construct irrationals using a compass and straightedge. Let's see how. First, we construct a square. Not just any square, but a unit square, with sides exactly 1 unit long. Now draw the diagonal from the bottom left corner to the top right corner. This diagonal is the hypotenuse of a right triangle with legs of length 1 and 1. Now apply the Pythagorean theorem. 1 squared plus 1 squared equals a diagonal squared. That's 1 plus 1 equals 2 equals diagonal squared. So the diagonal has length square root 2. We need to measure this diagonal and transfer that length to the number line. Now position the number line so it shares the same origin as our square. The 0 point of the number line is at the bottom left corner of the square. Take the compass, set its width to exactly the length of the diagonal. This is the critical step. Now with the compass needle at the origin and the pencil set to the diagonal's length, sweep the arc down to intersect the number line. That intersection point is exactly where square root 2 lives on the number line, at approximately 1.414. This is profound. We've geometrically constructed an irrational number. We've located it precisely on the number line using only a compass and straightedge. This proves irrationals are real. They exist in a concrete geometric sense, even though we can never express them as fractions. This same method works for any square root. If you want to construct square root 3, build a rectangle with sides 1 and the square root of 2 you just found. The diagonal gives you square root of 3. The ancient Greeks didn't have algebra as we do, but they had geometry, and geometry proved irrationals were undeniably real. Let's take a journey down the number line and see how all the number types fit together. We'll start simple and build up layer by layer. First, the natural numbers. These are the counting numbers 1, 2, 3, 4, 5. They appear as green dots on the line. Now we add 0, which wasn't in natural numbers. This gives us the whole numbers 0, 1, 2, 3, 4, 5. Now the line extends to the left. We add negative numbers, -1, -2, -3 and so on. This complete set is the integers. But so far we've only marked a few spots on the line. What about everything in between? Let's zoom into the region between 0 and 1. In this small space between 0 and 1, we now reveal fractions. 1/2 appears here, 1/3 here, 2/3 here, 1/4, 3/4, 1/5 and more. These are the rational numbers. Let's zoom in even deeper. Look at the tiny space between 0 and 1/2. Even in this smaller space, there are fractions. 1/3 of 0 to 1/2, 1/4, 1/5, 1/6, 1/7. More and more as we go deeper. This is the density of rationals, infinite fractions in every tiny space. Now here's the mystery. Even with all these fractions packed so densely, they don't fill the entire line. Look at what remains, gaps. And in those gaps live irrationals. Zoom back out to see the full picture. We'll mark some famous irrational numbers. Here's square root 2 at approximately 1.414. Here's root 3 and pi at approximately 3.14. Here's the fundamental truth. Every single point on the real number line is either rational or irrational. There are no gaps, there are no undefined points. The entire line is filled. Between any two rationals, an irrational exists. Between any two irrationals, infinitely many rationals exist. They interleave perfectly, creating the mathematical continuum that is the real number line, a complete unified system. Thank you so much for staying with me on this incredible journey through the number universe. You now understand something that took mathematicians centuries to discover and prove. Every point on this infinite line, every number you'll ever use, fits into one of these beautiful categories we explored together. Keep asking questions, keep exploring. Mathematics is everywhere, and you're now better equipped to see it. If you found this helpful, please subscribe, like, and share this with fellow learners. See you in the next video.